All right, everybody, welcome. It is Amber Whitney with Archery Review. We've got just one more minute before 11 o'clock hits. So thank you for joining all of us here for our chemistry test prep. So today we're going to go ahead and break down the chemistry content that is covered on your exam. But just remember, today it's a free webinar. It's very surface level. And don't forget to hop back on Friday with me at the same time, 11 o'clock, because we are going to put all of your learning and knowledge about chemistry to the test, where we will go through practice question after practice question, providing rationales for what the answers are and why these answers aren't correct. So put that in your calendar if you haven't already, and if you are able to join me. Again, that would be Friday at 11 a.m. So just 2 days from now, just checking in to see how you retain your chemistry knowledge. So as we wait for a few more minutes for people to join, I just want to share with you guys what all we offer you here at Archer Review. We have built a phenomenal question bank. I know you guys all love your practice questions. We have over 2,000 practice questions built in our Q bank right now, and you have the availability to check that out for free with a free demo. So that's a 24-hour free access to our question bank. And our next piece here on this list are on-demand videos. So with our 24-hour free demo, you would not only just get access to 2,000 questions in our question bank, you would also get access to these on-demand videos. So these are videos that do a deep dive into each area of each content. So for example, today we're going to do chemistry, and our first lesson in chemistry is the atom. So I'm going to give you very skim the surface level knowledge about the atom today. But in our on-demand video, you are going to get a much deeper dive into that lesson, and you are able to watch it at your own speed. You are able to, jump ahead to certain topics within that video that are time-stamped to really help you hone in as an individual learner. What are your needs? What are your strengths? And maybe just touch up on those, but then spend more time in the video for those areas that you need greater help on. But also in our on-demand videos, you have notes that are available to you, and you have cheat sheets that are available to you, which we are starting to show you guys little previews of on our social media. So make sure that you are following us. I'll jump ahead to that slide since I'm talking about it anyway. Make sure you are following us on Instagram. Make sure you are following us on TikTok and on Facebook. And of course, throw your email in there too so you can get stuff added to your calendar. But follow us on these socials because we give you previews of our cheat sheets, of our notes, of our webinars, and you're able to just, stay in the know with all things so that you are your most prepared self for acing your exam. Okay, so that's our Q bank, that's our on-demand videos. And again, remember that's a 24-hour free demo period. So scan those QR codes right now, guys. I don't know what you're waiting for. You can have access to those goodies right now for 24 hours for free. But beyond the free demo, we also offer tutoring, and tutoring can be included in one of our passes that we talk about down below. So you can either sign up for tutoring individually, scan that QR code now, you'll have access to 3 of our tutors in all areas, or we can talk about tutoring in a great package that we offer you at Archer Review. So let's do that for next. We have 2 packages here that you guys can join in on with us. And I know, guys, when you are in the depths of school and you're not only studying, most of us are working jobs on top of school, and money can be tight. I have been there. These packages, though, are affordable, everybody. And what you get for the price is just unbeatable. So Our first package here is the Sure Pass package. So I just talked about our Q Bank and our on-demand videos. This is what you would have access to beyond the free 24-hour period. And trust me, you're going to want a whole lot more than just a free 24-hour period to get the most out of these resources. So this Sure Pass option, Q Bank, on-demand video, beyond the 24 hours. All right. But then our Sure Pass Pro option, you still get the Q Bank, you still get the on-demand video access, but what's included in this is an hour of tutoring for you to use however you see fit in whatever area you want. It doesn't have to just be science, because I'm a science educator. It can be with math, it can be with reading, whatever your needs are. You get an hour of tutoring included in this. And I will say, signing up for this package here with that free hour of tutoring built in does save you a little bit of money in the long run, as opposed to, just doing the Sure Pass, thinking you're going to be okay with QBank and on-demand videos. And then you realize, oh, I would really love, just to have an hour of tutoring to clarify some of these things before my exam. And then you pay for the tutor separate. You can do that. But having that built in to that Sure Pass Pro option right away will just save you a little bit of money, as opposed to, that other route that I just explained. Okay, so it is 5 minutes in. Hopefully people are hopped on. Can you go ahead and just share with me in the chats where you are tuning in from? I always like to ask and see how widely distributed we all are as we tune in together for our, late morning webinar session. All right. Just checking the chats here. And as you guys share online, just a reminder for right now, if you are sharing anything in the chats on Zoom, you guys, I am the only one who is able to see your responses there. Okay, so if you're tuning in on Zoom, I am the only one able to see your responses. If you are joining me from Instagram or YouTube or Facebook, that is public. So I just want everyone to know that as we begin sharing out. All right. Just checking to make sure everything's good before we start. Okay. If you are on right now and you don't want to share where you're tuning in from, can you at least give me a thumbs up that we are live? Okay. All right. Let's go ahead and begin with atomic structure. All right. Let's go ahead and begin with atomic structure. I think I am. Oh, sorry guys. I think I was having both audio going at the same time from a different restream and it echoed on me. All right, guys. Officially, now let's go ahead and start. Let's begin with atomic structure. So let's start with atoms. Atoms are the basis of all matter. They're the smallest building blocks of all matter. And so atoms go ahead and make up elements. Elements are the different types of matter that you can find on your periodic table, for example, like oxygen or nitrogen or phosphorus or calcium. All of those elements are made up of atoms. So atoms make up elements. Elements will make up molecules. A molecule is like two or more atoms of that element held together by bonds. Then molecules go on to make compounds. So what's the difference between a molecule and a compound? Well, a compound is a molecule, but it's formed by having like different types of atoms, different types of molecules chemically bonded together. So a compound, you might have a little bit of oxygen, a little bit of nitrogen, a little bit of sodium. You have different types of those molecules or atoms bonded together. And then a compound goes on to make a mixture, and this is just a combination of stuff that's not chemically together, but like rather physically intertwined. And then mixtures are just, one way to describe different types of matter. So atoms make up all matter. Matter is everything in our universe. So atoms, so that's the basis of all matter. Like, okay, what's an atom made up of then? Well, we call the parts of an atom subatomic particles, and those you're probably very familiar with. They are protons, neutrons, and electrons. Protons have a charge of +1, +1. Neutrons are neutral, so we have a charge of 0 there. And then electrons have a charge of -1. So protons are positive, neutrons are no charge, and electrons have a negative charge. Let's talk more about each one of those in the following slides. The key concept for protons is that the proton defines what that atom is. Okay, so the proton number tells you the atom that you're looking at. And that number of protons is known as the atomic number because, again, the number of protons tells you what that atom is. So it's called the atomic number. Why do protons matter, though? Not only, I mean, only, they determine that atom, that element. They are the identifier for that atom. So if we change the protons, we end up changing the element. Electrons and neutrons that are also a part of that atom, they can vary. That will give rise to ions and isotopes that we'll talk here in just a bit. But the proton number itself must stay the same in order for it to be that element. So for example, if we're looking at an atom with one proton and one proton only, you're looking at the element hydrogen. So the atomic number is 1. If you're looking at a proton with 6 protons, like our visual here, you are looking at the atom carbon. So the atomic number is 6. If you're looking at an atom that has 8 protons, you're actually looking at oxygen, and the atomic number for oxygen is 8. I hope you see the pattern there. So if we change the protons, we change the element. Moving into neutrons. Neutrons are also that subatomic particle, but they don't have a charge. Remember, they are neutral, and we find them in the inside of that atom and within the nucleus. Also, we would find protons here. So inside the nucleus of an atom, we would find protons, but then we would also find these neutrons. Neutrons, a little bit heavier than protons. Remember, their charge is neutral, located in the nucleus. But what's the big deal about these neutrons? What is their job? They actually provide stability. So they are there almost as like a buffer. They prevent protons from repelling and fighting with one another. It just provides stability. But then neutrons, once you start messing around with the number of neutrons inside that nucleus of an atom, that determines isotopes. And again, I said I'll talk more about isotopes on a later slide, but isotopes, just a quick rundown here. They are helpful in medicine when it comes to like imaging and detection of tumors, for example. Isotopes are the same. It's that element. Like if we're looking at an isotope of carbon, it's still carbon we're looking at, but maybe that atomic mass has changed ever so slightly because we've added some neutrons or we took away some neutrons. But because we didn't change the protons, it's still the same element. Okay. But as we alter those neutrons, that radioactive decay of that atom starts to change its decay rate. And that's what makes it so helpful in the science world. Let's move on to electrons, the third subatomic particle. Electrons are negatively charged and they are not found in the nucleus with protons and neutrons. They are found orbiting the nucleus. All right. So when we talk about where electrons exist, you might hear that placement called orbitals. You might hear it called shells. Those words are interchangeable. But electrons buzz around that nucleus like busy bodies, always moving constantly. But I do want to talk about shells or orbitals real quick because it does help us understand where electrons are placed, which then helps us a whole lot when we talk about chemical reactions. Okay, so electrons fill from the innermost shell first. So you would be able to know, how many shells an atom has based on the trends in the periodic table. And we go into all of that kind of knowledge more in our on-demand videos. So if you feel like there's a learning gap right now, how do I know how many shells? You're right, you're not getting that in this webinar right now. That's some nitty-gritty detail stuff. So find that in our on-demand video, sign up for that 24-hour demo. But our shells fill up from the inside, the innermost shell first, and then fills the shells moving outwards. So for helium, it only has one shell. So that innermost shell, it is full. It can only hold 2 electrons. No matter what atom you're looking at, that innermost shell can only hold 2 electrons. And then as atoms have more electrons than just 2 of them, they start to fill the next outer shell, and then the next outer shell until all the electrons that atom has are placed in the orbitals that they have. So the role of an electron in an atom helps determine its chemical properties and its chemical reactivity. It is directly involved with bonds, chemical bonding. That is the job of electrons. It's involved in chemical bonding. But there's a certain kind of electron that are the major players when it comes to chemical bonding, and those are the valence electrons. Valence electrons are the electrons found in the outermost shell. In the outermost shell. So for helium, who only has one shell, these are its valence electrons right here. But in carbon, who has more than one shell, these 2 and that innermost shell here for carbon, nope, those aren't the valence electrons. The valence electrons for carbon are these 4 in that outermost shell. And then take a look at neon. Neon only has 2 shells, like carbon, but notice how it has more valence electrons in its outermost shell because it just has more electrons a part of that atom. So electrons, specifically valence electrons, these are the electrons that will be shared with other atoms. These are the electrons that will be lost or gained with other atoms, not that innermost shell for those who have more than one shell, okay? All right, ions. If we are exchanging electrons, if we give electrons away, if we take electrons on, these atoms now become what are called ions. And ions just means that this atom is no longer like neutral or stable. It like no longer has this equal amount of protons and electrons. There is a different ratio now. Maybe there's more electrons than protons. Maybe there's less electrons than protons. Whatever that shift is, gives that atom an overall charge. Okay, it gives that atom a charge. That's what an ion is. So there's 2 types of ions. There's cations and there's anions. Cations lose electrons. And remember, electrons have a negative charge. So if this atom gets rid of negatively charged particles, that makes that atom overall more positive. More positive. To help me remember that, I use this play on words here, this last bullet point. I am a cat lady. I got a couple cats. I love my cats. So when I hear positive, cations are positive. Think of like cat's paws because of the word cat and cation, and they're positive, like little kitty paws making biscuits. So that's just a cute little play on words that I use to help me remember cation. Or you can also think cation with that T as a plus sign. So that would also help you remember a cation has a positive charge versus or opposed to an anion. An anion is a negatively charged ion. These gain electrons. So if it's taking on more electrons and electrons have an overall negative charge, that means that overall ion is going to be negatively charged. they are going to have more electrons than they do protons. So, what determines if something gains electrons or loses electrons? Honestly, it's determined based on, how many shells it has, how many electrons are filling that outermost shell. Is it easier for that atom to just gain a couple more electrons, have that full outer shell, be stable, be happy? Or is it more wise, energy-wise, to just lose a couple of electrons, get rid of that outermost shell, and then just have that second innermost shell full of electrons? So that is explained more in depth in our on-demand videos, but there is how we determine cation versus anion. Finally, if all of this can be shared with us from the periodic table, let's do a quick review on how to read elements on a periodic table. So if we blow up, let's say oxygen, this little symbol here on the periodic table for oxygen, the symbol itself, we see the big letter O, that is telling us what the atom is. It's O for oxygen. Some of the letters make sense. They're just the first letter of that element. Some of the symbols are a little different compared to what the element name is, because I believe it was all developed using Latin. So the symbol shows your specific type of atom. You'll also see an atomic number on an element symbol. This is always going to be the lesser of the two values. And I say that because some element symbols will have the atomic number versus the atomic mass number in different places. So you can't always go off of, oh, the atomic number is on the top and the atomic mass is on the bottom. It kind of gets shifted around. So if you remember that the atomic number is the lesser of the two, that will help you distinguish which one is what. And the atomic number tells you what the atom is because it's telling you the number of protons that that element has. So oxygen with an atomic number of 8, that's telling you it's going to have 8 protons in the nucleus of that atom. But this other number here, the bigger number of the two, this we call the atomic mass. For oxygen, it has the atomic mass 16. This value not only includes the number of protons, but it's also including the number of neutrons in that atomic mass. So found in the nucleus, this is telling you how many protons and neutrons together. All right, moving into our second topic, physical properties and changes of matter. And I'm not seeing a whole lot of buzz so far on socials in the chat, and that's probably just because you are sitting and getting. But if you could go ahead and give me just a quick little thumbs up so that I once again can just make sure that everybody is hearing, we are live, we are good to go, you're learning all the things. If I could just get some thumbs up to verify for me, that would be awesome. Okay, let's go ahead and move into physical properties of matter. Remember, atoms make up matter, and matter makes up everything in our physical, in our natural world. So let's talk about some properties of matter then. Matter has mass, of course. Mass measures the amount of matter that takes up that object. So it's just whatever kind of object you're looking at, there's, a number of particles, there's a number of stuff making up that object. And so mass just measures how much of that stuff is making up that object or your substance. Volume is another physical property of matter, and this measures the amount of space that object or substance takes up. Because for certain substances, particles can be like really, really packed together. Particles can be like more widely spread apart, and that difference would change the amount of space it takes up, right? The volume could shift. So volume is how much space that takes up. Next up then is density. And density is just taking the previous two and dividing them by each other. So mass divided by volume, that is density. And again, density is telling you how tightly packed together those atomic particles are, or maybe, how widely spread out those particles are. That's density. So matter can exist in various states: solids, liquids, and gases. Solids, on the atomic level, the particles are really tightly packed together and they have energy. So they do like vibrate in place, but they're not crazy bouncing off the walls. It's a solid. So particles are tightly packed together. Solids have definite shape and definite volume because these particles are tightly packed together. Both shape and volume are definite. Liquids have a little bit more energy going on inside this state of matter. Liquids are a little more loosely packed particles. See the difference in our visual here. Solids tightly dense or tightly packed together, pretty dense. Liquids are less dense. These particles are a little more free flowing. They slide past one another. They have more movement. And so, because of this, they don't have a definite shape. Instead, they take on whatever shape of the container that that liquid is in. But it does have a definite volume. All right, moving up a notch, adding more energy, we get gas. Gas particles have the most energy of them all. And so these particles are far apart and they're moving around rapidly. There's no definite shape here because they're so crazy, and there's no definite volume for gas. But as you know, states of matter can shift from one phase to another. So it looks like there's a whole lot going on in this visual, but let's go ahead and just follow one set of arrows at a time. So let's start with the light blue arrows on the solid side. So if we're in solid phase, we can turn that solid into a liquid phase by melting. So how do we melt? We add heat. Think of like an ice cube out on a sidewalk here in the Midwest. It's starting to get warm here. Summer is finally starting to make its way in. We're about 90 degrees today, where we've been, like in the cool 65, 70 degrees. So if I were to put an ice cube out on my driveway and let the sun hit it with that 90-degree power today, we're adding heat. And what do you think is going to happen to that solid ice cube? It's going to melt. It's going to become liquid water. There's just going to be a puddle there on the driveway, right? And as that sun continues to bake even more, adding more and more heat, that liquid water is eventually going to boil and it's going to become a vapor, a water vapor. Until, you don't even see a spot on the driveway anymore. That water is not gone. I want to clarify that because matter can never be created or destroyed. It just exists in a gas state. Okay, and then sometimes it's, not as often we see this, but solids can skip that liquid phase altogether and become gas. This is called sublimation. So a great example of this is if any of you have ever worked with dry ice before. Dry ice, as soon as you see that solid cube of dry ice, it just sublimes instantly into that carbon dioxide gas. You can see it emitting right off of it, that vapor. Okay, let's go ahead and go the other direction. So let's do the dark arrows. Let's start on the gas side this time. So we're in gas and we remove heat. Okay, so if we are removing heat, we are removing energy. And if we're removing energy, then those particles, those crazy gas particles that are rambunctious, take some energy away from them. What's going to happen? Well, they slow down a little bit. They become a liquid. A gas becoming a liquid where those particles don't have as much energy, that is called condensation. Gas becomes liquid. Think about like condensation on a window or like on a drink, like a cold drink that sits outside. What starts to happen? The air around it, that gas starts to condense on the outer portion of your water bottle, and it forms those liquid drops. That's condensation. But then as we remove even more heat, okay, so we're in liquid state, we remove more heat, we turn it into a solid. It's called freezing. You take, liquid water, you fill up a ice cube tray, put it in your freezer. What happens over the next day? That liquid water becomes solid ice cubes. We removed heat from it. But then gas can sometimes jump straight to the solid state, skipping that liquid state altogether. So gas jumping all the way to solid is called deposition. And an example of this that I think most people are familiar with, but it depends on where you live, of course, frost. So frost forming on different surfaces. This is an example of gas going to a solid, where that water vapor in the air directly transforms itself into ice. All right, let's go ahead and move into our next section, describing chemical reactions. In order to describe chemical reactions, we got to come back and talk about valence electrons. I told you these are the major players in a chemical reaction. So valence electrons determine an atom's reactivity and ability to form bonds. It all comes down to valence electrons, people. Atoms will always try as much as they can to achieve this stable state of where, like, their outermost electron shell, remember that's where the valence electrons live, wherever, or their outermost shell, they want that shell to be full. Okay, so most outer shells are going to hold 8, unless you're like hydrogen and helium, who only have that one shell, it can only hold 2. Okay, but all other shells can hold 8. So atoms are constantly trying to achieve this state of stability by getting 8 electrons. They can do that by either taking on electrons. Remember how we talked about anions? They're going to take electrons to fill that outermost shell, or they recognize, like, hey, like, I only have 2 in this outermost shell. Instead of getting 6, oh, that sounds exhausting. Let's just go ahead and get rid of 2, the only 2 we have in our outermost shell. And then, we don't have that outermost shell anymore. Now we're just down to that next innermost shell, which is full. So there's, that either gain or loss of electrons. But no matter which circumstance, we're talking about valence electrons. All right. So just remember that atoms that lose valence electrons, they're going to become cations or positive ions. And typically these are going to be metals. Metals on the periodic table are going to be on that left side primarily. So you can see alkali, alkaline, transition metals. These ones are going to typically lose valence electrons. They'd rather lose them, get rid of them, and in return, they become a positively charged ion. But then on this side of the periodic table, you've got nonmetals. Nonmetals tend to gain valence electrons, which means that they become negative ions because they're adding more negatively charged stuff to their atom in order to become stable. So ionic bonds versus covalent bonds. Ionic, we already know that word, ion. Ion means loss or gain of electrons. Okay, so this is just simply looking at the bond that occurs due to those shifts in electrons. So when one atom loses an electron and another atom gains an electron, that is the ionic bond. Typically, this occurs between a metal and a non-metal. So going back to the periodic table, typically we're looking at an atom on the left side bonding with an atom on the right-hand side, a metal bonding with a non-metal. And that ends up with a cation bonding with an anion. Those opposite charges attract, creating that ionic bond. That is different than a covalent bond. So in covalent, you see the prefix co. We know that with like co-teaching, co-parenting. You do it together, right? It's a shared responsibility. And then valent just refers to valence electrons. So valence electrons together create a bond. So covalent bonds share these valence electrons. They're not giving them away. They're not gaining them. They're sharing them. There's like an overlap happening here between these two atoms. The covalent bond typically occurs between non-metals. And when this bond is created, it creates polar molecules, meaning that some electrons are going to be a little more heavily distributed on one end of the molecule as opposed to another end. Okay, moving into chemical equations. Chemical equations are chemical reactions. We just express them mathematically. So how can we get someone to understand or demonstrate a chemical reaction? We use chemical equations. So the basis of a chemical equation, you've got reactants that form products. Reactants are the starting materials. Products are the ending materials. Reactions, chemical equations, don't always go in that forward direction. Sometimes they can go in the reverse direction. And sometimes they can go in both directions at the same time. More on that in our on-demand videos if that's an area that you feel you need greater understanding in. And remember, 24-hour free demo period. There's no reason for you to not sign up, right? So make sure that you do. So we've got reactants that become products. But what's really important when we are showing chemical reactions is that chemical reactions or chemical equations should be balanced. And what I mean by that is this: matter is not created or destroyed. It just takes on different forms. So however, how much stuff I have in the reactant side, I need that exact same amount of stuff in my product side. It just might be rearranged, might take on a different form, but it is still present. And so we have to show that using math. So you're going to see different numbers in a chemical equation. And I want you to know the difference between the two because only one of them you can change, the other one you cannot. Subscripts. Subscripts are the little itty bitty numbers followed like after an atom, and they're going to be like down below that atom. So see how CH4, the 4 is down below the H and it comes after the H. This is indicating to you the number of atoms of that element in a molecule. So for CH4, we've got 1 carbon because there's no number after it, so we just assume 1. And in our visual, you see the 1 carbon. And then since it says H4, that's telling you that there are 4 hydrogens around that carbon. We cannot change subscripts in chemical equations. Cannot. If we do, we end up changing the entire molecule. We're no longer talking about the same type of matter, and we have to account for all parts of matter. This is different, though, than coefficients. Coefficients are this big number out in front of that entire molecule. It's telling you how many NaCl's do you have? Do you just have 1? No, we have 2 NaCl's. So coefficients tells you the number of molecules in total you're working with. This does not change the molecule itself, right? We're not changing Na being bonded with Cl. That remains the same. We're just changing how much of that there is. And this, coefficients, this is what you do change when balancing chemical equations. All right, so let's go ahead and just work out balancing a chemical equation together. Remember, only changing the coefficients. So first, what I like to do when I see a chemical equation is I like to take inventory. So I count up how many of each part of the atom on the reactant side I have versus how many I see on the product side. So for hydrogen, you can see that there are 2 hydrogens on the reactant side and there's 2 hydrogens on the product side. Good, that's balanced. There are 2 oxygens on the reactant side and I only count 1 oxygen on the product side. This is not balanced. So you have to start manipulating the coefficients. So I have these blanks here for you to fill in and work out using basic math, some multiplication. How can I get 2 oxygens on the left side to match 2 oxygens on the right side? So with this coefficient out in front, what can I multiply this 1 oxygen by to get it to equal 2, like the left-hand side? Hopefully you're thinking, well, you know what, Amber Whitney, 1 and I got to get to 2, so I multiply by 2. It's that easy. Put a 2 coefficient out in front of water on that product side. Now, it's important to remember that these coefficients are like the distributive property in math. This coefficient not only applies to oxygen, so 2 times 1 oxygen, we've got our 2 oxygens now. That's happening, but that 2 is also in front of the hydrogen. It's also going to manipulate the number of hydrogens because it manipulates the entire molecule. So 2 times 1 oxygen, we've got 2 oxygens. 2 times 2 hydrogens, because we have to multiply by that subscript, 2 times 2 hydrogens now means I have 4 hydrogens on the product side. So our oxygens are equal, 2 on this side, 2 on that side. But you know what I notice? What's not equal? These hydrogens. We've got 4 hydrogens on the product side and only 2 hydrogens on the reactant side. So think quick mental math here. How many should I multiply this hydrogen on the reactant side by to get these 2 to equal 4? I need it to be 4. I need it to match the product side. So from 2 to 4, what can I do for multiplication to get 2 to 4? And there's your answer. Hopefully you were thinking 2 times 2 equals 4. So now we finally have a balanced equation. We've got our coefficient of 2 in front of H2. That gives us 4 hydrogens on the reactant side, 4 hydrogens on the product side. We have 2 oxygens on the reactant side and 2 oxygens on the product side. We have just balanced our chemical equation. But remember the importance of it. It's not just, a math game. It represents the law of conservation of mass. Matter is not created and it is not destroyed. We have the same number of matter on both sides of that chemical equation. All right, let's move into conditions affecting chemical reactions. We got about 20 minutes left. I think we're doing great on time. So conditions that affect chemical reactions. Talking about the chemical reactions that we just went over, ionic bonds, covalent bonds, chemical equations, we can alter the rate of those chemical reactions by playing around with a few things. So the factors that affect those reaction rates are concentration, pressure, if we're only talking about gases, that is, temperature, and catalyst. These 4 factors can change the reaction rate. All right, so let's talk about how. If we have a higher reactant concentration, so let's say, you're going to make a batch of cookies. Maybe this is a good analogy for you. If you are settling for, I'm just going to make 1 batch of chocolate chip cookies. Let's, that just sounds good. Let's see how much stuff we've got in the cupboards and in the fridge. And then you find out, well, wait a second. I've got, double the amount of eggs. And this economy, that's a big deal. Let's maximize on that. So if we've got, more reactants, more stuff that we start off with than what we realized, and you're like, well, why settle for 1 batch of cookies when you can make 2 batch of cookies? If you have more reactants, you're going to make more products. Same thing in chemistry, because cooking is chemistry, by the way. So if you have more reactants, you're going to end up with more products. This is going to occur because you've got more collisions, more stuff available to collide with one another. And if they're colliding with one another more frequently, that leads to a faster reaction. For pressure, and again, this applies for gases only, so this factor of pressure will only affect gas chemical reaction rates. But if you have higher pressure, you're putting those particles closer together. So think gas laws. The higher the pressure that you have, maybe you have, like a smaller volume, for example, you're making those particles collide more frequently because they're closer together, and that's going to lead to a faster reaction rate. Temperature, if we alter the temperature, you are certainly going to alter the reaction rate. If you increase temperature, which simply just means you're increasing the energy, you're going to have particles colliding around more. That's more kinetic energy. And if they're colliding around more, they're going to have a faster reaction rate. But you can also do the opposite. If you reduce temperature, we remove that kinetic energy, we remove that heat, particles are going to slow down. And so if we slow down the collisions, you're going to have a slower reaction rate. Catalyst, our final factor here. Catalyst lowers activation energy. All right, so activation energy means how much energy does this chemical reaction need to even start? Well, if a catalyst is present, it lowers the amount of energy it needs to even begin. So your reaction rate is going to occur quickly. It's going to be sped up. What's important to remember about a catalyst, though, is that it's present, but it is not used in a chemical reaction. Okay, let's move into equilibrium. Equilibrium occurs when chemical reaction reaches this state of balance. And by balance, I mean that the rate of reactants becoming products or products going back to reactants, it is equal. It's the rate that is equal. They're going and proceeding at the same rate. I don't mean that they have equal amounts of stuff or equal concentrations. That does not have to be equal. But their rate itself, how fast are they going from reactants to products and then products back to reactants? That rate is equal. And that's known as chemical equilibrium. But Le Chatelier's principle helps us make predictions about this equilibrium when it responds to a disturbance because, chemical reactions in our body, for example, they're not in equilibrium for long. Your body is constantly being bombarded to stimulants, changes in pressure, changes in temperature, and your body has to respond to that. And so as soon as that equilibrium is disturbed, and you know how it's disturbed, it can be predicted how the chemical reaction responds. That's called Le Chatelier's principle. So let's break that down quick. Le Chatelier's principle, like I said, is just teaching us that when a reaction is at equilibrium and that equilibrium is disturbed, things will start to adjust itself to get back to equilibrium. So if the temperature is changed, so let's say an endothermic reaction is taking place and the body is absorbing heat, so we're increasing temperature, we are going to shift that equilibrium to the right. Because as we said in the previous couple slides, if you increase temperature, that's increasing energy. And if you're increasing energy in particles, particles are going to be reacting like more quickly, colliding, bombarding with each other. So if those reactants are colliding more frequently, of course you're going to end up with more products, right? So it's shifting that reaction to the right. The opposite side, though, temperature can be exothermic, meaning that it is releasing heat. Okay, so if we are releasing heat, we are going to shift that equilibrium to the left, favoring reactants, not making as many products and favoring the reactant side. We can also mess around with pressure, like we said. So increasing pressure shifts the equilibrium toward the side with fewer moles of gas. And if we decrease the pressure, this shifts the side with to the side with more moles of gas. So we've got decrease in pressure, more moles of gas, increasing pressure, it's going to shift to fewer moles of gas. And then finally, catalysts. Catalysts speed up your equilibrium, but they don't shift that equilibrium position. Because remember, catalysts just have to be present to lower the activation energy rate. So it's just making that reaction more attainable, but it's not going to shift the equilibrium balance overall. Okay, let's move into properties of solutions. Our second to last topic today. Solutions. Solutions are a mixture where two or more substances are evenly distributed. So this means that the solution, it's a homogeneous mixture. Think of like milk. In milk, you've got water, you've got, sugars, you've got some fats and proteins, but you can't see all of those particles, right? They're evenly distributed. That's a solution. As opposed to like the classic example for everybody is always like Italian dressing. And Italian dressing is going to have, big chunky particles. You got to shake up that Italian dressing before you put it on your salad because you want it to be mixed up well. Solutions are homogeneous. They're not like Italian dressing. And in a solution, you have a solvent and a solute. The solvent is the stuff doing the dissolving to the solute. Typically, this is water because water is a universal solvent. Solute is a substance that dissolves in the solvent. Okay, so this is the stuff that is being mixed into water, for example. There are three different types of solutions you may come across. There is unsaturated solution, meaning that there's not as much solute as what could be, right? There's more solvents available. It could dissolve even more solutes in that solution. That's called unsaturated. A saturated solution has the maximum amount of solute that can be dissolved in that solution. And a super saturated solution, meaning that it has gone beyond what is typically able to be dissolved. But this is unique because it has to have a higher temperature present. So more solute is able to be dissolved beyond that saturated solution state, but you have to have a higher temperature in order to achieve that. That brings me to water, because water is a universal solvent. Water, being the universal solvent, has unique characteristics, which I think is amazing to study because these qualities we're about to talk about right now is literally what allows life to be able to exist. So water is a polar molecule. Take a look at the visual we have of water here on the right, right? H2O. So we've got our H2s, 2 hydrogens, 1 oxygen. But what I mean by water being polar is that when we talk about the distribution of those electrons in chemical bonds, we've got this side of this water molecule that has, a little bit more electrons grouped on this end, as opposed to this side of the water molecule where we don't have electrons, on this side of that molecule. So you have this polarity occurring, right? Like polar, like north, south pole, opposite sides of this molecule too, negative versus positive. Because of these partial positive changes, this allows water to easily form hydrogen bonds, meaning that this negative end of oxygen is going to have an attraction to another positive part of another water molecule. And this hydrogen here, this positive charge that's partially present, is going to have a strong attraction to a negative element, such as, another oxygen nearby. That's going to be your hydrogen bonding. And that is what gives water its unique properties, like cohesion and adhesion. Cohesion means that water molecules stick together. They stick to itself. This is very important for the blood flowing through your veins right now. Blood is about 90% water, 90% water. And if it didn't have this ability to stick to itself, blood would just separate into all of these tiny droplets. And so cohesion, water, this attraction with hydrogen bonds, it allows water to stick to itself and for blood to be able to flow through your veins and arteries right now. But then there's also adhesion. Adhesion is when water sticks to other things, not to itself. That's cohesion. Adhesion is water sticking to other stuff. So this is really important when we talk about, things beyond just our own bodies. This is for how water gets up through the roots and in through the stems and the leaves of plants, for example. Like capillary action, which is applicable to blood in our body too. It helps it adhere to, or helps our blood adhere to our blood vessels, a different substance, the blood vessels. And it also helps in wound healing. It allows the blood to adhere to a wound so it can clot and eventually heal. So how do things move about in living biological systems? It can be broken down into 2 different transportation systems: passive transport, active transport. And to summarize, I'm not going to read all this. You guys can read it for yourselves. But to summarize this, passive transport moves from areas of high concentration into low concentration and does not require energy. Think of lighting a candle, spraying some perfume or cologne. It's highly concentrated in that one spot where it's all densely packed together. But as you add heat, like burning a candle, those particles will diffuse out into the air where there was no smelly substances before, at least, from the candle itself. So diffusion is one way to show passive transport, and diffusion is moving of particles from high to low concentrations with no energy. Active transport, on the other hand, it's the opposite. Active transport does require energy. This is moving particles against the grain. You're taking particles in an area where there's not that many and you're moving those particles into an area where there has already been plenty particles. It's like you're going to open a floodgate. Well, when you open that gate, what's going to happen? All those particles that are numerous are going to naturally want to flow out, diffusion. But in active transport, you're there like fighting that herd, pushing them back into that gate, not letting those particles escape. And while you're at it, here's a few more. That's active transport. And that does require energy to fight that natural flow. Osmosis is one final method of transportation that I'll go ahead and mention, and it's strictly regarding water. So it's the movement of water from high to low concentration across a membrane. So that is going to be like diffusion, right? High to low, no energy used here, but it's specifically for water. Okay, we are down to about 5-6 minutes left, and we've got one more topic to cover. I think our timing is still going great. And if you stick around at the end, I'll talk more about some really awesome resources that we have here for you as a learner at Archer Review to help you be the most prepared as you can be on your pre-nursing journey. Let's go ahead and wrap up with acids and bases, which, by the way, we covered on our socials this week. So if you follow us on Instagram or TikTok or Facebook, you got to see some of this teaching already with these visuals. We showed you our cheat sheet we created from this content. And if you don't know what I'm talking about, here's your plug to go follow us on socials so you can get some of this content taught to you for free week to week. So let's talk about pH. pH is the potential of hydrogen. It measures how acidic or basic a solution is using a scale from 0 to 14. So whatever kind of solution you're working with, is this acidic? Is it neutral? Is it basic? You will know by reading, the pH value. So something that is acidic will have a pH less than 7. So that's going to be from, 0 to 6 on the pH scale. So take a look at some of these examples. We've got battery acid as our most acidic option here. Stomach acid with a close second, then lemon juice, vinegar, black coffee. Black coffee is, a little acidic. So anything that is acidic has a value less than 7. But what does that mean? It's acidic. Okay, well, if in a solution, these atoms, these components of this matter are going to naturally break off these hydrogens. We call them hydrogen ions because you see that charge there. We know ions have a charge. These types of substances release and give off these hydrogen ions when they're dissolved in water. And because it releases these hydrogens, that will overall make that solution more acidic. So that's why it's considered an acidic solution. Oh, stumbling on my words here. That's different than neutral, which is, a great example is just pure water here. So we're not talking about, like spring water or tap water. We're talking about pure water that should have a pH of 7. And then bases are going to be anywhere from 8 to 14 on your pH scale. And, like acids, they release something when they are dissolving in water, but it doesn't release a hydrogen ion. That's the job of an acid. Instead, a base releases hydroxide ions, these OH negatives. And so as you watch that substance, let's say bleach, for example, get dissolved in water, you would see these OHs breaking off and dissolving in the water, making that overall solution more basic. But we also have neutralization reactions, and these are really, really important, in your own bodies, for example. Neutralization reactions occur when an acid reacts with a base. So we've got like hydrochloric acid, for example, which can be found in your stomach, reacting with sodium hydroxide, a strong base. When an acid, a strong acid, reacts with a base, in this case, a strong base, it will always, always, always form a salt and water. You're looking at a neutralization reaction when you see a salt and a water on that product side, because this acid mixing with the base will make a salt and a water. And this is going to typically lead to a neutral solution. So on the pH scale, we're talking about a pH of 7. But for your salt, keep in mind, you're not always going to see sodium chloride for your salt. That's just the type of salt that was created because of what our reactants were. You are oftentimes going to see other forms of salt. All right, everybody. That is the end of our very surface level chemistry cat crash course. I know there are more things that you guys could dive into deeper. I hope throughout this webinar, you were able to recognize what are you really, really good at? Like, what do you already know? And what are some things that, you felt like, oh, I haven't talked about that for a while, or I haven't freshened up on that knowledge, and I really need to. I hope you did, because that's going to give you some direction when you navigate through our on-demand videos. So remember, you guys have a 24-hour free demo period to our question bank and our on-demand videos. And in that Q bank, you know what? I'm just going to go ahead and share my screen. Let's get out of this. I'll take you directly to our website. How is that? Okay, so when you get to Archer Review, you're going to want to sign in, go to our dashboard. When you're in the dashboard and you're signed up for this free 24-hour demo, you're going to have access to our QBank. So in our QBank, there are statistics that are tracked for you to help you keep track of what the questions you do well at, you rock, and questions that you missed and you need to, go back through and do again. So you can create a test. You can have it timed so it mimics, your exam environment. And you can choose through, so let's do chemistry, because we just did chemistry, right? So let's do chemistry, click next. And let's say through today, you realize like atomic structure, protons, neutrons, electrons, I got that. Don't need questions over it. Cool. But when it comes to chemical reactions, oof, like I really need some help there. Or those, the conditions that affect chemical reactions like temperature and catalysts. So choose the stuff that you need. You can individualize everything here to cater your needs. Create a test. And our platform will mimic your test exam environment. All right. So look, there's one of 45 questions. Just between those two topics, you got 45 questions to practice with. Okay, so let's end test. Yes, I want to end. And let's take a look at our on-demand videos. So also included in that 24-hour free demo are our on-demand videos. And right here at the top, you can see that you can choose between your different content areas. So just like I did with Question Bank, I'm going to go to science. Let's choose chemistry. And right here, notice how you've got different like subsections for each major topic. This is called timestamps. So like I said earlier, let's say, atomic structure, totally get it. Don't need to spend time on that video. Let's jump to chemical reactions. And, ionic covalent, I really understand those two. I don't want to watch 4 minutes of that video that I already know really, really well. I want to jump right to chemical equations and get to the stuff that, I really need help with, or like balancing chemical equations. So I click on chemical equations and the video starts.
Electrons play a huge.
And also included in this video are a handout. So you have access to all of the notes, all of these slides here. You can print them off with, like lines off to the side for you to annotate, take your own notes as you're listening through this. And we have cheat sheets. Cheat sheets are these beautiful, like 1 or 2 pagers that give you all of the essential information covered in those slides. Okay. So we've got some really, really fantastic resources available for you guys. So if you haven't already, check out our 24-hour free period for our on-demand and question bank. I'm going to go ahead and pop up those QR codes for you. so you can get access to those. Let me adjust my screen here so it doesn't look so messy. Okay, I'm not gonna fiddle around with adjusting this too much. Okay, so here are those QR codes for that. Don't forget about tutoring. If you need access to a tutor, scan the QR code. You can sign up there. If you want to check out more free live webinars, and I hope you do, they're free, people. Sign up. We have free ones going on all the time. And you know what, guys? This week, I think we're record breakers. In the pre-nursing sector, we've got 9 free webinars for you this week. So we're halfway through this week now. It's Wednesday, but we've got more coming at you the rest of this week. And don't forget, I specifically will be back with you Friday, 11 o'clock Central Time, to take all of this learning we just covered today and just go through practice question after practice question after practice question with you. So don't forget to get signed up for that. But let's say you're like, oh no, I'm not going to make it Friday, but I really want to watch that webinar, or I just want to go back and see, what all you guys have covered over the months, the years with our free webinars. So here's our rewatch webinars. This QR code is going to take you to our archived webinar library, all previously recorded stuff. These are awesome. These are great, you guys, but they are surface level. Remember, our on-demand goes into much more detail for you. So, yep, free webinars, those are so awesome. It keeps knowledge fresh, but our on-demand is even better. And then finally, our 2 packages. So if this all sounds awesome, great, I need this to be successful, to pass my exams, and maybe to just study throughout your pre-nursing journey, check out our Sure Pass option and our Sure Pass Pro option. Sure Pass is going to give you our QBank and on-demand video access well beyond that 24-hour period. Sure Pass Pro is going to have the QBank and on-demand videos, but an hour of tutoring included in there as well. So here are those QR codes for those 2 packages, all right? All right, I'm going to leave those QR codes up for just a minute. And then finally, before you guys hop off, I do have one QR code that I'm asking everybody to scan. All right, I'll give people a minute to sort through their QR codes at the moment. Your Sure Pass Pros, your Sure Pass, your free webinar, all the stuff. Get it sorted and get your camera back out, because our camera app back out and ready, because I would appreciate your guys' feedback. So if you could scan this QR code and give me some feedback as an educator for you guys on this chemistry webinar, but then also maybe just some feedback about anything else that you guys may need to share some feedback on. Go ahead and answer this survey for us about the webinar to help us, be our best for you. We are here to serve you, our future nurses, in your pre-nursing journey right now. But at Archer, we have resources to support you well beyond your pre-nursing journey, whether it's, to pass your nursing boards, whether you want to go into advanced practice. We have it all. So this is the start of it all, though. So please scan the QR code, give us some feedback on this webinar so we can be our best selves for you all. I'm going to go ahead and leave the QR code here for all of our other products. And if you have any questions, please feel free to share in the chats and I'll help you out. I'll be live for about 1 or 2 more minutes as necessary. All right, everyone. I do not see any questions popping up, so I think that concludes our webinar for today. Thank you all for joining us, and don't forget, check back in with me Friday, 11 o'clock Central Time to do all the practice questions over this content. Have a beautiful Wednesday, everybody. Bye.